Hello and welcome. This is Brandon Burton with the Restoration Sciences Academy. I want to thank you for joining us today for this presentation on psychrometry. One of our advanced series will specifically focus on airflow. To begin the discussion today, as we have with some of our previous modules, I'd like to begin with a quick review of some of the information that builds up to today's subject. In an earlier module, we discussed the calculation for evaporation rates, and we learned a couple of very critical points in this calculation that are relevant to today's discussion. Most importantly, when we look at any peer-reviewed calculation for evaporation rates from materials, there are several consistencies in those calculations. Mainly, when we look at airflow, measured typically in velocity as either meters per second or similar, we notice that the variable for airflow is a multiplier in the calculation. You'll notice it in this calculation represented by this symbol immediately after the equal sign. And in this expression, it is a multiplier of the other factors, namely the amount of moisture in air, the amount of moisture in the material, and the vapor pressures associated with those. What this tells us is that the movement of air across a wet surface has a dramatic impact on the ability to remove water from a material and that surface. What's critical about this calculation, however, that we're going to dig into a bit deeper today, is this air movement, this airflow, is not only critical in its speed, where the airflow exists is also very critical. In other words, air movement in the air above a material is not nearly as impactful as air that actually contacts the material. And we'll take a closer look at that as we get into some of the more advanced understandings and topics related to airflow. There are other factors, obviously, in the calculation that are important to evaporation rates, and these are expressed in a number of different measurements depending upon the group that you have a discussion with and what their background is and their application. In our industry, in water damage restoration and damage repair, we typically state this as a humidity ratio. It's measured in grams of moisture per kilogram of air. It's the most common expression that we're going to see. It's also expressed as dew point, sometimes expressed as vapor pressure, and these are all units of measure that basically express the same thing, just from a different perspective. They're all specific measurements of the amount of moisture in a given air sample. In some of the previous discussions, we began to take an advanced look at psychrometry from the aspect of humidity. And we did discuss things like humidity ratio and dew point and vapor pressure, and how all of these are a relationship to energy. And at the end of the day, what causes evaporation, drying, or any change for that matter to occur is when we do have differences in energy. So just as a quick review of that topic, and then we'll move into airflow. When we look at a psychrometric chart, which is the typical instrument that we'll use to understand psychrometric principles in a drying environment, we can calculate for any one of these principles. And what we're looking at on screen right now is a measured temperature of 15 degrees Celsius at a saturation, meaning 100% humidity or completely wet, full of moisture. Where these points intersect on the chart at 15 degrees and saturation, we can see over here on the right-hand side of the chart a couple of different calculations, and one of these being the vapor pressure associated with the water vapor in that sample. In order for that water vapor to move from one location to another, whether it's from one room to the next, from the outdoor environment to the indoor, or even from a building material into the surrounding air, better known as drying, there has to be a difference in that vapor pressure and that around it. And when we look at a psychrometric chart, we can evaluate these different conditions in these different places. For example, let's say that we had a building material that was in this same environment that had a temperature of 30 degrees Celsius. So the material is warmer than the surrounding air. In addition, that building material is completely saturated. It's wet. It's visibly wet. It would be wet to the touch. Liquid water is present in the building material. At that same condition, our vapor pressure in that material would be substantially higher. This would be a difference in energy and would cause drying to occur. And the greater this difference is, like anything else in science, the greater the reaction will be. For a better discussion on this and understanding how to apply this, look at some of the earlier modules that we have up on the website, and you can see a full discussion on how to understand vapor pressure differentials. But moving forward, let's talk a little bit about airflow. And we're going to start in an odd place to talk about airflow. We're going to start with a microscope. What we're looking at here under a microscope is we're taking a look at a sample of softwood. This is just from standard softwood framing material, but this would be representative of most wood materials. We're looking at a 40 times magnification, and the wood is in a water solution. That's why you see all the water bubbles, or the air bubbles rather, around the image from the microscope. What I want to call your attention to is the cellular structure that we see in the wood. And notice these dark areas and light areas. To understand what that is, I'm going to magnify this, and we're going to go to 80 times magnification. Here we're looking at the cellular structure of the wood, and you're looking at the cavities inside of the cells that comprise the wood. The reason why you see darker and lighter areas inside of these cavities, just to point this out, is that because you've got water and air both inside these cavities. And just like this bubble we see up here on the screen, you can see the air bubbles that are trapped within these cell cavities. So what does that mean? What that means is that a lot of the moisture that we're targeting in wood is a liquid water that is trapped inside of these cell cavities. And this is critical to understanding the role that air movement and vapor pressure, for that matter, play in a drying process. But to make better sense of it, let's go to a drawing of the same. So here we've got the cellular structures that we were just taking a look at under the microscope. And inside of these cellular structures, we see that we have liquid water present. To explain how water moves through building materials, let's take a look at some of the other structures that we see on these cells. There are small dark areas on the walls of the cell, commonly referred to as a diaphragm. And these are areas where moisture can move from one cell to the next. If this was a natural living growing tree, for example, then capillary action would cause water to be drawn up this cell, and as this cell filled, water then would be transferred to the next cell and then drawn further up the tree. And this is a process that we refer to as a component, at least, of something called transpiration, as water moves up through the living organism. Why is that important to you and I? We're trying to get water to move through the wood in much the same way that it moves through the wood in a natural drying process. And in order to do that, we've got to understand these mechanisms for how water moves. The drying process is, in other words, going to utilize these same movement systems or these same mechanisms. We're going to evaporate water from the surface cells, and as we do, we have to have liquid water then move through the wood from one cell to the next to continue the process. Taking a look at that mechanically in a drying process, when we provide air movement over the surface of wood, this liquid water is going to readily evaporate from these surface cells. And as it does, it's critical that air movement is there to rapidly remove that evaporating water. If we do not, then this water will build at the surface. We'll end up with something that we call kind of loosely a boundary layer, which interpretation for that would mean an area right at the surface of the material where air is not really moving that quickly, and the humidity begins to build because nothing is moving it away from the surface. This builds a vapor pressure at the surface, and it begins to impede additional evaporation from the building material. So the closer we orient our air movement and the more directly our air movement touches the surface, the more we can break up this layer and allow additional evaporation to occur. Now, this is the process that we see with free water, liquid water, inside of cell cavities. This evaporation process is going to be exceptionally rapid. And to verify that we are using air movement appropriately, one of the most critical things that we need to do at this stage is we need to measure the humidity at the surface of these materials to validate that we have enough airflow. This is pretty simple to accomplish. If we simply take a hygrometer at any stage in the drying project, we can verify whether or not we have enough airflow by simply placing the hygrometer's humidity measuring element directly in contact with the surface of a building material and evaluate that humidity from a relative humidity measurement. And let's say, for example, we measure this humidity and we achieve a measurement of 40% relative humidity. We then take the same hygrometer and measure the air mass above the building material and verify these are consistent. If the humidity in the building is at 40% and the humidity on the surface is at 40%, both are the same, then you're providing enough airflow. However, if the humidity at the surface of the building material is higher, even marginally higher, 45, 46, 47% relative humidity, then you are not supplying enough air movement. In other words, the humidity in the balance of the room is irrelevant. That is not the moisture content that is allowing for evaporation. That's not the dryness that is impacting your evaporation rate. The only air that is influencing evaporation is the air that is directly contacting the building material. This sounds very simple, but it's highly critical and very commonly overlooked. And if this one principle is not applied, then we'll see dramatic reduction in our drying rates with building materials. Now, this evaluates the importance of air movement on a very simplistic level. In other words, we're talking about a surface that's directly available to our air movers. If we think about building construction, there are many surfaces where evaporation is occurring where the surface is not immediately available to my air movement. So application of this concept can become complex depending upon the surfaces that we're trying to target in the drying process. But not only does that make it a bit more complex, let's go one layer deeper into the drying process and see how else it becomes more complex. As we remove the easy free water from the building material, eventually what we're beginning to tackle is something that we call bound water. Using wood again as the example building material, bound water is defined as the moisture that is chemically bonded to the cellular structure of the wood. In other words, this is not water that is inside of the cell cavity. This is water that's actually bonded within the cellular wall itself. Now, this moisture has two problems in the drying process. Not only do we need to remove the moisture from the actual physical wood item, we also have to release the water molecule from its bond with the wood product itself. So there are two stages in this drying process. This first stage, releasing the water molecule from its bond with the actual wood, is not an air movement process at all. In fact, air movement will have virtually no impact at all at dislodging that molecule in the middle of a piece of wood. The only thing that's going to dislodge this molecule is a difference in energy in the wood. In other words, we need to again rely on the earlier concept discussed of vapor pressure. There has to be enough energy in the actual water molecule, in the wood itself, and lower energy in the surrounding air spaces inside the wood, in the cavities, in the pores, etc. This can only be leveraged with the discussion that we had in our earlier module. To jump over this for now, however, air movement does still have a role in this process, but its role is dramatically diminished. It's still important, and we still can evaluate whether or not we have enough air movement in place using the same type of measurement. Simply take a thermal hygrometer and place that hygrometer along the surface of a building material that we are targeting, that we're drying, and verify that the humidity at that surface is the same as the humidity in the balance of the room. What you'll notice when you take this measurement is that you can significantly reduce the amount of air movement that you're using and still achieve that same humidity at both surface and the air above the surface. It does not take as much flow. Most studies and most peer-reviewed documents will show a reduction of about 70% in airflow and still be able to maintain that balance from the free water drying phase versus the bound water drying phase. If you want to go out and do some research on the topic, very commonly in the building science community, the material science community, they're going to refer the difference between these as what they call the constant drying rate versus the falling drying rate. Constant drying rate being when we're dealing with the free water, the liquid water, and the falling rate being when we're dealing with the bound water. So what does all that mean? Tying all this together and moving this into more of an application perspective in an actual water damaged environment. Let's take a look for a moment at a relatively simple building schematic and just analyze for a moment where some of these conversations about air movement moving along the surface can be critical. Of course, the most obvious is along the actual finished surfaces within the interior built environment. Whether this is carpeted or we have some other type of a hard surface building material, if moisture exists in that material or in the materials immediately in contact with it, then air movement along the surface will be important. The amount of air movement can be evaluated using a hygrometer. Simply placing a hygrometer on the surface of the wet material will verify that we have enough air moving across that surface. Substantially higher humidities at that surface mean you don't have enough. Add more. Just this one adjustment in and of itself will have a dramatic impact on your overall drying times. However, we have to think a bit more forensically and look deeper into the structure and look at some of the other surfaces that may be at play. The second most obvious in this particular schematic is in this space we see in the exterior wall assembly. Here, very commonly, we can have a substantial amount of moisture depending upon the nature of construction, especially when we're dealing with this type of a slab construction. Because you'll notice here that the plane within this cavity is actually lower than the concrete plane in the balance of the space. Here, it's very easy for us to end up with a high amount of moisture that can be affecting not only the concrete foundation, but also the interior facing stonework and masonry. If we do not get airflow into this space, then the drying rate on this lower area of the brick can be substantially impeded. How much airflow is needed here can be evaluated again in much the same way that we evaluated the flooring surface. The trick is to get a hygrometer into the space. I'll show you a couple of methods of measurement for doing this here in just a moment, but measuring the humidity in this cavity and verifying that that humidity is the same as the humidity wherever your drying resources are, your dehumidification, will verify that you have enough air movement. If the humidity in that cavity, in other words, is 90% or 80% relative humidity, then it doesn't matter what your dehumidification systems have created inside the living space. That air is not impacting that assembly, and it's going to dry slow. It's going to take weeks upon weeks to dry those building materials. However, if I can get the humidity in that cavity down to 20, 30% relative, then the drying process will be dramatically faster. There are lots of ways to use hygrometers to measure different types of surfaces, to evaluate whether or not the humidity is appropriate in those areas. Just several examples here of some creative hygrometer use. Just run through each one of these and describe what's being done. Here we have a hygrometer that is underneath a plastic sheet. And there are lots of varieties of plastic that would work for this. Any standard low permeance or non-permeable plastic sheeting will work. The only requirement that I'd give you is make sure that the plastic sheeting is clear, because we're going to put a hygrometer underneath that plastic sheet, and we want to be able to see the display. This method of measurement traps the moisture to the surface so that we can get a measurement of how wet the building material is. And this is a pretty common measurement. It's something that we discussed again earlier as we discussed vapor pressure of building materials. This is another measurement where we're actually putting the probe inside of a dense material. Here we're evaluating again how much moisture is in the material based on the humidity that's being created. Again, down below, several alternate methods for doing much the same thing. These are all very precise measurements of humidity that are used to understand how wet a building material is. And believe it or not, the measurements that we're talking about can be much simpler than this. The containment, the holes, etc., are not necessary when you're evaluating airflow. All you need to do is simply place the hygrometer on the surface of the building material and allow the hygrometer sensing element to measure the moisture at that surface. If the, again, humidity at the surface is higher than the humidity in the balance of the room, then we're not applying enough air movement to that surface. It's a very, very simple measurement. The measurement can be completed with a good hygrometer, at least. It can be completed in a matter of seconds. It's not something that we're going to have to wait several hours for acclimation on. With that measurement in play, if you provide more air movement until these humidity measurements are the same, I guarantee you're going to get a much faster drying rate than if they're not. So taking that concept and moving into kind of the same model here that we've closed many of these discussions with, There are three components of your psychrometry, if you will, that influence evaporation rates in a building environment. They are humidity, airflow, and temperature. Throughout a series of modules here, we've discussed either at a basic level and some at a more advanced level, the role and influence of each of these types of measurement. Initially, in a drying environment, we start with very high concentrations of moisture. Building materials are at or near saturation. Liquid water is visible sometimes at the surface of these building materials. During this stage of drying, something we call the constant drying rate, the emphasis should be on a very high rate of airflow over and on in contact with the actual wet surface. This by far is going to be the most impactful mechanism to allow you to speed drying rates. This single tool implemented properly can cut a drying rate by over 90% versus a drying process where it has not been implemented properly. Humidity and temperature are still important in this stage, but quite honestly, the reason why humidity and temperature are important are only to prevent damage to unaffected materials. As we're rapidly evaporating this water from the surface of these very wet materials, it's critical that we don't allow humidity to elevate to a point where unaffected materials begin to absorb water. Generally, as a benchmark, we use a 60% relative humidity target for this number. Keep the humidity at or below 60% to prevent that damage. Now, as we move past the really easy surface type water, we're still dealing with very easy liquid water with the free water phase that we discussed just a moment ago. And in this stage, again, air movement is still really critical. But as we begin to evacuate the water from the cells and pores and cavities in these building materials, and no liquid water remains, the impact of airflow becomes exceptionally diminished. At this point, at this stage, what becomes critical is a continued focus on the reduction of the air's moisture content, which will lower its vapor pressure, and a continued focus, where appropriate, on elevating the building material's vapor pressure. Again, we've discussed both of these concepts in earlier modules, and they will be discussed again in more advanced application as we move forward with our modules throughout this year. When we leverage these properly, the overall impact on our drying times and our drying rates are extremely dramatic. Without the application of air movement in the front side of the process, drying rates are exceptionally slow. They're a natural drying rate. Building materials without the implementation of airflow initially are going to dry at the same rate as if basically a restoration contractor had not been engaged at all. With the application of airflow, reduction in drying time can easily be 40 or 50%, and in some cases up to 90% reduction. As we moved into the second stage with a focus on humidity and vapor pressure differentials, again, we can impact the latter stage of the drying process, the falling drying rate. With appropriate application, again, we can have dramatic reduction. 40 to 50% reduction in drying times can easily be achieved. So hopefully this information on airflow is helpful for you. We do have some additional modules that will be coming up throughout the year. We're going to get into some building material science in our next module, helping us understand the specific building materials that we encounter in the restoration environment and some of their unique nuances. There are definitely some very specific considerations that we need to make based on the type of building material. And it's not just on the obvious, on the density, etc. There are many other characteristics to these building materials that are important. So I look forward to you joining us for that module. And with that, thank you again. This is Brandon Burton with Restoration Sciences Academy, and we thank you for joining us for our webinar series.